Okay, and we'll get this panel started. Hello, my name is Ray Mizgorski. I'm with Carnegie Mellon's Career and Professional Development Center, and welcome to Campus Engagement Day. Today's session is going to feature speakers from programs at the university that prepare students for careers in hardware, robotics, and controls. Each speaker will present a little about their department program, and then we'll turn it over to the employers for the Q&A part of this program. For the presentation portion, please keep your microphones muted, and please save your questions for the Q&A. Thank you. I would like to introduce today's speakers. We have Aaron Johnson from Mechanical Engineering. We also have Mark Budnik from Electrical and Computer Engineering. And finally, we have Reed Simmons from the Robotics Institute. Aaron, would you like to start us off?
Sure thing. Let me get this all shared here. All right, hopefully that's showing up for everyone. Might have some Zoom issues. Let's see. Am I still connected?
Yeah, we could still hear you, but it's not showing.
Okay. Well, why don't you go with someone else and I will restart my computer here.
Okay, you want to try next, Mark?
I would be happy to. If I may share my screen.
Yeah.
All right, can you see the lovely PowerPoint presentation?
Yes.
Good afternoon, everyone. My name is Mark Budnik. I am a newer teaching professor at Carnegie Mellon University. Prior to entering into academia, I graduated from the University of Illinois back in 1990 with my bachelor's degree and immediately started working in the semiconductor industry with companies like SGS Thompson back then, Hitachi, Infineon, National Semiconductor / Texas Instruments. And I really fell in love with developing my young engineering teams and teaching them all the things that I wasn't taught back when I was in school. And that eventually led me back into getting my master's and PhD and entering into the academic fields again. And I'm really excited about this first year that I've had back at Carnegie Mellon and being able to take what I think that I've been able to bring back from the industry into the classroom and really excite and motivate the students for what I think has been something that's been lacking from a lot of different schools around the country for a long time. CMU is obviously at the leading edge of so many things, and I'm glad I'm here to make it even better. Within our electrical and computer engineering department, we have a mission like everybody else, and you can see it written there on the left, I hope, to inspire, educate, and produce electrical and computer engineers. After that, what I'd really like to tell you essentially is that we're trying to develop our students within three basic focus areas in terms of technical expertise, an ability to innovate, and also ability to lead. Now, not all of our students right out of school are going to become leaders, but we want them to be able to take the role of leadership on if necessary, because I recognize that by the time that they're 22 or 23 years old and perhaps in the industry for 6 months or a year, they may suddenly become the expert in the room in one small area that they need to be able to talk about and explain rationally. And along with that, the idea of being an innovator. When I was in the industry, I spent a lot of time in the field applications roles and working with our customers. And we had a phrase that we oftentimes discuss with our customers about being able to design their way out of a wet paper bag. And we really want our students to be able to holistically understand the design process, look for places for improvements and opportunities for new developments and innovations. Our department, by the numbers, you can see here, we break it into two separate sections for students, undergraduate and graduate. The way that we count students at Carnegie Mellon, at least within our College of Engineering, is that we don't typically roll in the freshman students or first year students, because they're essentially an open field of engineering students to be. They've not necessarily declared what their major or what department they're going to be in yet. But if we roll them into what are eventually going to become our EC students, we stand at 500 second, third, fourth year students as undergrads, around 650 grad students, and a total cast and crew of around 275 between faculty members and staff members. We are growing, which is something that not a lot of different EC programs are doing around the country, but we're pretty excited about that. And I like to think that we're also growing in the right way. You can see there are two of the topics that are really important to me. The number of students in our department in college that identify as women has continued to grow. ECE is up to 40% this year, and I believe our college overall is slightly above that this year. And our underrepresented minorities, we're continuing to work on that. It's up to around 20% right now. This is a challenge that we're going to continue to fight for many, many years as we are dealing with the problems that students are having or facing before they become college students, and trying to make sure that we're providing the resources necessary.
Set up something for us. Can you not do 4:30?
Hello?
Okay.
James, looks like you had your mic on. I couldn't tell. Were you asking a question?
No, sir. Sorry about that.
Okay. Ideally, again, finding ways to reach out to programs around the country to better prepare the students before they get to Carnegie Mellon, and make sure that we have programs in place so that anybody that comes here and wants to be successful in electrical and computer engineering can be. We have a curriculum that's a little bit different within our EC department than many other schools. We have a very narrow list of core courses that everybody takes. The 18 prefixes are prefix for electrical and computer engineering. The 5 courses are the 100, 213, 220, 240, and 290. The 100 is a traditional introductory first year class in electrical and computer engineering. And then essentially after that, we have an introductory or primer course in programming, hardware, analog hardware, digital hardware, and then signals and systems. And then from that point, our students really are going to be designing their own curriculum from that point on based upon what their interests are. And these are the 5 different areas that we really focus on within our electrical and computer engineering curriculum. Specifically today in the hardware robotics controls group that we're discussing with you today, these are the 3 primary areas that the students are going to be looking at: signals and systems, circuits, and hardware systems. The really great thing about this curriculum is that by the time they get through these 5 core courses, they have a solid understanding of the basics, but they can really now delve into the things that they're really getting excited about. And it allows us to develop students at the bachelor's and master's level far beyond anything I've seen before when a student comes out of college, because it's something they've really been able to focus in on for 2 years or more in their class studies. And just as an example, this is one of the different whiteboard talks that I was giving in one of my classes, where we were actually combining a lot of these different topics in signal systems, circuits, and hardware, where the students were given an open-ended design challenge for a project to develop an industrial automation system to maximize the throughput through the system, while also being able to maintain the safety regulations they had to deal with. And then they also had to work with the fact that it must survive any single point of failure that I wanted to put into the system. So I told them that I might unplug the power, or I might go ahead and disconnect a sensor or an actuator, or maybe all of a sudden a microcontroller was going to lock up. And their system was going to have to be able to survive and ensure the safety and integrity of the physical manifestation of the system beyond that. And we really built the system up from that point there, allowing us to go into much more detail in terms of what really goes on in a design behind the scenes. It's not just, here's a simple assignment, go back and write your 13 lines of code or build a circuit and go ahead and demonstrate it for us. It really was a multi-long week project of getting them to do research, learn what's out there, give them the opportunity to explore what different types of sensor technologies and actuators they could play with. And again, get them to the opportunity that they have the chance to find out what they're excited about, and then hopefully get connected into the areas that you all are going to be interested in as prospective employers down the road. The facilities we have within our College of Engineering across the board are outstanding. Within ECE, we have a number of different resources. The bottom right building is actually our Hammerschlag Hall. That's primarily the residence for ECE, but we have other places around campus. Going counterclockwise in the top right, this is Scott Hall, which is home to a lot of work that some of my colleagues are doing in other departments, but is also home to some of the Engineering Accelerator Research Program in our nanotechnology building. The ANSYS Hall in the top left-hand corner over here, which is shared a lot with our mechanical engineering comrades and colleagues, and also looking at our making spaces. And then the new building coming in the bottom left here, our SCAFE Hall, which is well under construction and is soon to be opening in the next 12 months, I believe, which is going to provide even more meeting, collaborative, and project workspace for our students, because the idea we want here is that we want to get students out of the traditional classroom setting and into a place where they can actually be building, making, doing, and creating the world of tomorrow, whether it is software, whether it's hardware, or whether it's going to be a full-blown manifested system. Last thing I just want to touch base here in this very short introduction is that there's lots of opportunities for student organizations and groups to get engaged with different parts of the industry. We have a growing number of corporations and nonprofits that are working with us in a couple different ways. The most common way is that corporations, industries are sponsoring small little student projects, anywhere from 1-2 students to teams of 10 or 12, and they may last anywhere from 4 weeks to a year or two. There is a tracking system that we use that students can basically find out at any given time what is available and what they can get into. They can express what their interests are. We get to review the students to see what their capabilities are. They have to provide a resume for stuff like this, and then we can actually work with our corporate partners to find and identify students that might be of most interest to you as a prospective partner to Carnegie Mellon. It's really meant to be something that's going to be driven by the corporations and the students. We're here to facilitate it and to make sure that things go smoothly, but it's really meant to be an opportunity for the students to become closer to you and your businesses. Then over here on the right, we have a couple different pictures of things that I thought would be interesting to you. The top right corner is from our Maker Fair. It's called Build 18. Again, 18, the prefix for electrical and computer engineering at Carnegie Mellon University. Hundreds of students gather over a week's time to basically perform their favorite hackathon type of activities. It's a great big show. A couple different projects that I thought were really keen from the last couple of years. The one in the middle on the right is a system that actually holds a book, and it would automatically turn each page and then scan each page and put it into a computer file. So really integrating a lot of different disciplines for finite manipulation of something as simple as a page, but at the same time be able to go ahead and provide some relatively advanced visualization and storage information. And then one down here on the bottom, again, a walking robot, not just a traditional car or wheels, but something that's actually going to be a little bit more that can actually navigate stairs and stuff like this. Lots of different opportunities, lots of different places for us to go. Again, what I'd really like to leave you with you as a summary is that we're really trying to focus our student development in electrical and computer engineering related to hardware, controls, and robotics in these 3 areas: technical experts, leaders, and innovators for tomorrow. Great. I think that was relatively close to 12 minutes.
Right on the money. Okay.
Awesome.
All right, Aaron, you want to try it again?
Yeah, all right. I think I just I think my internet cut out for a minute there, and then it wasn't happy with me. Unless this crashes the second time. So. All right, how's this looking?
Good.
All right, great. So thanks everyone for coming out. My name is Aaron Johnson. I'm in the Mechanical Engineering Department. I thought I'd just start with a quick sort of summary about me and what I do. So my main sort of research interest is in design and control of robots that go out into all sorts of challenging terrain, from dirt and woods to urban areas. In terms of teaching, I mostly teach dynamics classes, both undergrad and grad level, as well as I used to teach a robot design class. And then one of the things I wanted to make sure I mentioned right up front is that CMU is a very collaborative place. And so my home department is in mechanical engineering. I have a courtesy appointment in ECE. I have a courtesy appointment in robotics. I have grants and students shared with faculty all over campus. And actually my undergrad was at CMU as an ECE, and then now I'm in Meki. So we're sort of giving you these presentations as different departments, but we all kind of work together, and their boundaries are not as rigid as in some places. Some quick facts about the Meki Department. We have 40-something faculty, about 215, I think it's going up this year, it's PhD students, to a little bit more than that in terms of master's students, and then 365 undergraduate students. And as was mentioned before, undergrads, we don't count freshmen. So freshmen are sort of general engineering, so this is sort of sophomore through senior. So it comes out to about 120 a year. Some points we wanted to make about the sort of on the undergraduate side. We have a diverse student body. The diversity is sort of growing over time, with about 40% female students, which is very good, especially in mechanical engineering, sort of nationwide, and 28% URM. We have a lot of very active and strong student organizations, including ASME, Pi Tau Sigma, Women in Meki. We have had a very strong student-led mentoring program that was started this year that they've been really driving the way for. We're also sort of, in terms of overall numbers, we're the second largest department in engineering after electrical and computer engineering. Yeah, okay, so those are the same. Yeah, all right, so the the sort of curriculum philosophy we have is fundamentals with flexibility. So we have very strong fundamentals classes, but we think we're sort of unique in our ability to facilitate double majors and minors. So students can also choose to focus on a specialization within Meki or take a second major. And the two most common double majors are biomedical engineering, which at CMU is, I think, only a double major, and then robotics as well as a double major. And then a large number of minors from sort of all over campus. As I mentioned before, we have very strong student activities, and we sort of think of this as co-curricular, so in parallel to the curriculum. And I think of this as one of the real strengths at CMU. The CMU undergrads, they really love building things and tinkering with things, and we don't even list it here, but the two most popular undergraduate student activities campus-wide are Booth and Buggy at Carnival, which is building a sort of high-end soapbox derby car and then building a 2-story house for fun, in their extra time. And so, so many of the student activities are really engineering projects because that's sort of who they are. They like to build stuff. Some of the organizations here, the FSAE team is closely related to mechanical engineering, and they've been doing very well in the recent competitions. It's also CMU Rocket Command and a number of other projects. And I also want to take a moment and highlight this bottom point here, undergraduate research. 50% of our students, half of our undergraduate students participate in research at some point in their time at CMU. And I think this is one of the great strengths that we have. We make it very easy for students to get involved in the research labs. I can tell you in my lab, I've had something like, I don't know, I think I average about 10 or 12 students a year in my lab that working on, some of them working on independent projects, some of them working with PhD students or postdocs. Some of them, sometimes it's sort of larger teams, other times it's smaller teams, but I really enjoy getting them involved deeply with the research experience. We have this great space called TechSpark. So this is our Makerspace. It sort of spans the area between Hammerschlag Hall and ANSYS, if you're familiar with campus. And this is just sort of an amazing space that just came online. I guess it was right before the pandemic, so let's call it 2 to 3 years ago when it sort of fully came online. And this has all of our sort of our metal shop, wood shop, a whole wall, a couple walls worth of 3D printers and laser cutters and stuff for students to use. And a lot of the project classes will use this space. And I can tell you, if you come by Techspark near the end of the semester, you get this incredible energy and activity from, there'll be 30 different project teams working on stuff at the same time in the space, and it can support all of that activity, and really makes it easy for students to build a great prototype for those more project-based classes. To the undergrad destinations, so where do they go? Boeing, Tesla, GM, SpaceX, these are sort of the biggest ones. I can tell you, so I pulled out some top employers from my lab. I think SpaceX is the one that the most undergrads from my lab have gone to, but also Intuitive and Tesla and Shark Ninja and some of these other ones. And about half of our undergrads go on to do some form of continuing education. A lot of that is the integrated master's program, but also a number of them will go on to master's or PhD in other locations. Switching gears a little bit to the graduate curriculum. So the graduate program has about 250 master's students, just a little bit smaller than that in terms of PhD students. Let's say the 250 master's students, that's sort of a typical year. Due to some sort of COVID fluctuations, a number of students deferred. And so this coming class, 2022, 2023, will be a bit bigger than that actually, because a number of students sort of deferred around COVID. We have a sort of interdisciplinary research culture. Here's sort of the 6 main areas that we sort of organize our research in. But again, as I said, I work with other faculty and other students from all across campus, and that's true of just about every faculty member at CMU. On the graduate side, we have over 100 students in our research master's program. So that's a 2-year program where they come in and do a master's thesis, working with a faculty member in Meki or in other departments. And the majority of them, the master's students in that research program, really want to get research experience. But then, still I think 80%, looks like 80% go on to look for jobs after graduation. So some of them are coming in as a stepping stone to a PhD, but a lot of them are coming in because they want to get more involved in research so that they can get more sort of research R&D type jobs after they leave. They take, our graduate students take classes from all over campus, both within the College of Engineering and outside. I know pretty much all of the graduate students in my lab will take classes in computer science and robotics, but other departments as well. I wanted to pull out a few sort of classes in the sort of controls, robotics, and design space. That's the focus of this. And I know this is kind of an eye test, and so I won't be grading you on memorizing this, but here's some of the classes that we offer, and I wanted to highlight that we do have a number of graduate classes that are project classes that I think of as almost like master's capstone. So at the undergrad, we have sort of this idea of a capstone class at the end. It's pretty common in engineering education, especially for this Master's of Engineering, Master's of Science Engineering advanced study program. They're required to take 2 project classes. So we have a number of these sort of capstone-like classes sort of in the different areas. So what are some of those classes look like? So here's a video from a student project from the Advanced Control Systems Integration class. So this is sort of the capstone on the controls track of this quad rotor. If you watch the video in the upper left, there's a little dot here at the bottom, swinging back and forth, and it's trying to swing that ball up into a cup on top of the quad rotor there. So hopefully the video comes through on Zoom, but I think right here, yeah, it sort of loops it up and then is able to catch it in the top of the quad rotor there. another one, so one class that I designed and then I was taught by another faculty member is bio-inspired robot design and experimentation. So this is sort of the capstone in the robotics track, where over the course of a semester, students have to build a robot or at least a major component of a robot. And so here's one on the left of a microspine-enabled climbing robot, and on the right is this sort of flamingo-inspired walking robot. And I even take the students to the zoo at the beginning of the class to sort of generate some of these project ideas. Let's see, we also have a number of professional development elements in the different courses. Some specific courses where that are focused on professional development, and then also, like here again, the robot design and experimentation class that I taught. We bring in a faculty member from the English department to help them prepare presentations and their written documents for that. And so that's really sort of baked in throughout the curriculum. And then we've also had a number of companies that are involved in courses, and certainly a number of companies working in research. And so this can be for those either at the undergraduate or graduate level, more capstone-like project classes coming in, and sometimes a company will have put in a little blurb and say, like, here's a potential project that a project team will grab onto. And then other times they provide parts and supplies or sort of other ways that they can get involved in those classes. And then again, here's the sort of graduate student destinations and that kind of metrics. I can say from my lab, a lot of them go to Amazon Robotics, Boston Dynamics. A lot go into the car industry, Ford, GM, Waymo, as well as MathWorks, NASA, et cetera. And so with that, I think I'm probably over, but I'll pass the baton on.
Okay, thank you, Aaron. All right, we can move on to Reed. Are you ready to go?
Yes.
All right.
All right. My screen sharing?
Yes, you are. Looks good.
Okay, great. Thanks. Yeah, so somehow I got shoehorned into this robotics and controls and hardware. I'm going to be talking about the artificial intelligence program, which has relationships to robotics, but is also quite different. So we started a Bachelor of Science in Artificial Intelligence 4 years ago. Just yesterday, I guess 2 days ago, we graduated our first full cohort of AI graduates. That was 35 people. We decided 4 years ago that it was the right time to start the first in the nation standalone major in artificial intelligence. As we heard from both Mark and Aaron, the idea is to provide students with a comprehensive education in the area of artificial intelligence. And we're not training students merely to use the technology, but we're training the students to develop the next generation of technologies. Because of this, there's a strong emphasis in the program in ethics and social responsibility, given the position that artificial intelligence is going to exhibit in the future. So in today's society, AI is becoming more and more ubiquitous, everywhere from navigation systems, self-driving cars, medical, fraud detection, home use. And Andrew Ng, a prominent researcher in machine learning, has called artificial intelligence the new electricity, whereby I interpret what he means by that is that in the near future, AI is going to become as ubiquitous in our society as electricity, and we won't even notice that underlying all of our technology is some aspect of artificial intelligence, just like we don't really realize that electricity is powering all of our technology today. So what is the underlying technology that is used? we take a really broad view of artificial intelligence here at Carnegie Mellon. Many of the students coming in, all they know about artificial intelligence is deep learning, machine learning, but there's really so much more. Fundamentally, we deal with knowledge representation. So the world is full of data, but data is not knowledge. Knowledge is abstracting and collating that data into something meaningful that can be then manipulated by a problem-solving and decision-making system that can then impact the world. And machine learning does undergird all of this, but it's not the only aspect of AI that the program focuses on. And we don't think of AI as a standalone system. We think of it as a system that is integral with the rest of the world. We have courses in the program for understanding the world in terms of vision, natural language understanding, robotics, of course, and in particular, human AI interaction, because don't want to scare anybody, but we're not developing artificial intelligence to take over the world. We're developing artificial intelligence to help people in their daily lives and in their businesses. And because of that, human AI interaction is incredibly important. So when we put this all together, we have an architecture of intelligent agents that takes the hardware, sensor readings takes that information, that data, and converts it into knowledge in the perception system. Cognition then can act on that knowledge, producing actions that are then affected through hardware to change the world. And as I said, undergirding all of this is machine learning that is continuously operating to improve the resilience and the accuracy of the perception, cognition, and action components.
Reed,
Yes.
are your slides advancing?
Are they not?
No, I haven't,
Oh.
not what I can see.
Okay. Thank you. We'll start.
Sure.
We'll try sharing again. Okay.
Better.
All right. Thank you. We'll talk a little bit about the major itself. We are in the School of Computer Science, and so no, I can't. There we go. And so a solid core of computer science, math, and statistics is at the foundation of the program. But around that, we have two core areas, representation and reasoning and machine learning. And around those areas, we have four elective areas. Decision-making robotics relates to the cognition and action components of the diagram that I showed earlier. Perception and language, of course, is perception. Human AI interaction, again, we're looking at AI interacting with people as its most most of AI will be interacting with people. And then machine learning is both a cluster, an elective area and a core area because of its importance in artificial intelligence. And surrounding all of that is a ring of ethics and social responsibility. It's very interesting that we want to people, the developers to know, the students to know that not only do they need to behave ethically, but they need to develop systems that behave ethically as well. So here's a short presentation of the curriculum for the AI major. We have a strong, as I mentioned, core in math, statistics, and computer science. The computer science core courses are the same as what the computer science majors get. And then in addition, we have 3 core courses in artificial intelligence, 4 elective courses in AI, 2 courses that can be taken anywhere from the School of Computer Science, a course in ethics, and a course in either cognitive psychology or cognitive science. So we want students to understand that it's not just artificial intelligence they need to understand, but human intelligence as well. As I said, the program started 4 years ago, as both Aaron and Mark mentioned, with in College of Engineering. In School of Computer Science, students come in as undeclared majors their first year, so they're part of the AI major only from their sophomore year on. So we have, at this point, we have 146 majors including the 35 that I mentioned who just graduated, 23 graduates from prior years. And here's the breakdown. A large number go on to graduate school. This is quite a larger number than the School of Computer Science in general. We're still trying to understand exactly what the impetus of these students to go on to graduate school in larger numbers. 40% go on to the big tech companies, Google, Amazon, Facebook, Microsoft, and 20% go to smaller companies, to fintech companies and some startups. That's pretty much the breakdown. Besides the primary major in AI, we have a number of other things that students can study. So there's an additional major in AI that was just rolled out this past year. There's a minor in artificial intelligence that is geared towards students in less technical fields than computer science or math or ECE. And then there's minors in some areas related to AI, including machine learning, natural language processing, robotics, and human-computer interaction. And all of the above are open to all CMU students. And we get a fairly wide range of students who are interested in these areas from across the campus. And I want to close by talking about our Makerspace. So this is an AI Makerspace. It just opened in January. It is different in concept to the TechSpark case space that Aaron talked about. When you think about traditional makerspaces, you think about machine tools, laser cutters, 3D printers, lathes, and the students use that to build hardware widgets. Well, in the AI Makerspace, we give them the hardware widgets, robots, drones, AR and VR equipment, smart IoT, smart appliances. And what they're making is not more hardware, they're making intelligent agents. They're making software systems that can interact with people and do intelligent things. This is a makerspace that's open to the whole CMU community. In fact, it is located in the Tepper School of Business. And to be honest, we have business students coming down all the time, salivating over the prospect of interacting with some of these technical students to create the next billion-dollar business. So I think that's all that I have. And I guess we have a little bit of time for questions.
Okay. If you would like to unmute yourself and ask questions or place your questions into the chat, we can then ask the questions. So
Hi, can you hear me? I have a question. Okay, yeah, what I wanted to ask was, you have like, I had heard this student project tracker. So you have like a program where you allow, you have students doing a project with the corporation. And I just wanted to ask, is that happening during the semester, and is it in person or remote?
It is a combination of everything. It is primarily during the fall and the spring semesters, because most of our students go on to more full-time type internship work during the summer. For the last 2-3 semesters, it's almost all been remote type stuff, but we have a number of smaller companies in the Pittsburgh area that are doing it in person also at this point.
Okay, so if we wanted in person, like right now, we have several CMU students right now as we speak for our summer internship in person. And most of our projects are in person, so it would be difficult to do this during the school year then, right? The student project program.
For some projects, it would be more difficult to do so. Other times we have some companies that are saying, you know what, we want to go ahead and screen students in the fall, and then we'll take a select group of those in the spring, and they'll continue working on something remotely in the spring. And then everybody that works on it remotely in the spring will commit to doing an internship with us over the summer. So it's really a matter of, we want it to be as flexible as possible for you, because again, it is for, by, and with the students. We are simply trying to make that bridge between us and you. Carnegie Mellon is not trying to take on any intellectual property rights from the work that they're doing. or anything that you're sharing with the students. We're simply trying to make sure that the students have those opportunities to continue to grow and develop during this time. And I'd like to say is that we can make it as flexible as what you need to make it work.
Okay, and this could be, it's not just in ECE, right? It's also in AI and Meki, is that correct, this program? Or is it just ECE? The student
ECE has a
project?
program that's formalized, and mechanical engineering and the rest of the programs, I'm sure, have similar type things, but it may not be as formalized as what we've been doing in ECE. I'll let Aaron and Reed talk to their respective groups.
Oh, okay. All right. No, that sounds great then. And if we are interested in doing something like this, who would we contact in ECE?
You can go ahead and start with me, and I can get you in touch with anybody in the department head's office to get those up and running. Again, at any point in time, we may have anywhere between 10 and 30 projects that are waiting for additional students. And the more exciting your project is, the easier it is for us to populate it for you.
Yes. And is it for undergrad or grad or both?
Both.
Okay. All right. That sounds great. And we in fact, we hired one of your students that came as an intern last year, and he's going to be starting in a few weeks. So, and we also have other interns right now. So thank you very much.
You're welcome.
All right. So James put in a question in the chat.
Oh, I just
For the
responded in the
analog,
chat.
sorry?
I'm sorry, I just responded in the chat.
Oh,
But yes,
okay.
we do have classes where students will be doing IC design and fabrication they do the design in a semester, they fabricate, and then they have an opportunity to do the tests in basically a third type semester. Students could theoretically take the course out of sequence where they take the test first, and they may actually be doing tests on an IC they've not designed yet, or they could take just one or both depending upon what their interests are. A lot of that historically has been more on the digital side, and now working onto the mixed signal side. I'm not sure that I would ever call that one of those trips was truly a pure analog type circuit, but I would call it more digital and then digital into the mixed signal. If that answers your question, James.
It does. Where do you do your fabrication? Is this MOSIS, or are you guys contracting with somebody else?
We go through MOSIS on occasion, and then we have some partnerships with specific companies that actually will come to us and say, we're desperate for IC designers. We'll let them fabricate in our fabs if we can get students working with us. And similarly to the student tracker project, students can take that course, they get flagged as a fellow for that particular company, and it will tie back into, for example, take the design course in the spring, come intern with us in the summer, and then when you come back in the fall, you can test your chips.
Yeah, great. I definitely want to get access to some of your internships. This is, Infineon hasn't necessarily been a big player in the analog space, but we're trying to get there. I'd love to have the opportunity in the fall to speak with some of your interns.
I'd love to. I actually did a couple of years work with the Infineon facilities up in Livonia, Michigan, and the automotive is still near dear to my heart. So we'd love to talk about it.
All right. Sounds great. Should I contact you?
That is fine. And if I can't answer your questions for you, I will get you to the next person.
Excellent.
The right person. And I think that Lindsay's already put my website into the web page there. I can pop my email address in there also.
Great. Thanks.
Any other questions? All right. One question that I have is, what is the most popular skill that your students learn while at CMU that may not be directly taught in your class or program?
As funny as it sounds, I would say it's actually time management, because so many of our students come in raw from high school thinking that they can do everything and anything, and they can wait until the last minute before it has to be done. And what they realize very quickly is that's not true at almost any college or university. And at a place where we expect so much from them, we really get them to realize fairly early on they can't do everything for anybody anymore, and learning how to prioritize what they're excited and interested and focused on, and then also how to learn how to make smart, intelligent decisions, which are part of the engineering design process. And I think that's kind of get baked into the curriculum, and I only see that growing and developing more over the next couple of years.
So I would say similar to that, but collaboration. So A lot of the stuff that people are looking at, the systems are way too big for a single person to work on their own. And so a lot of the courses are project oriented. They learn collaboration skills. Again, time management is obviously important, but so is collaboration. So I think those are two of the more important soft skills that the students learn through the work here.
I have a question. Those are both good answers. I'll throw one more in. We just had an alumni come back and speak at graduation for in Meki, and he talked about sort of learning how to learn. He got out and he was surprised to find that the problems he was working on didn't just look like a textbook problem of find the mass of whatever, and so sort of figuring out how to learn what you don't know and get to the answer.
I have a question for you.
Go ahead, Robert.
And this is observational, not a complete study, but I work in the autonomous navigation ADAS space in automotive. And whether I'm talking to my colleagues who work at competitors, we're not all the same vicious competitors the press would make us out to be. At the OEMs, everybody, there's a massive shortage of people who work in the fields of computing science, electrical engineering, et cetera. How do you reconcile the planet's appetite for this talent versus the pipeline of engineering students available and soon to be graduates?
So I'll give you my 2 cents on it. There was a huge disservice after the bubble burst in 2000, where people became convinced that every software and electrical engineering job was going to be outsourced somewhere else in the world. And nationwide, we are still seeing a shortage, particularly in electrical and computer engineering. Computer science has been growing and growing, but unfortunately, in most schools, ECE is really on the decline. And those that have the software and hardware skills are very hard to come by. And it's almost become a self-fulfilling prophecy. I've had so many students that I've talked to that said, oh yeah, my high school guidance counselor told me to go into civil engineering because they told me that I might not be able to get a job because there won't be any electrical engineering jobs when I graduate, but we'll always need roads.
Really?
And I think that all we can do is continue to beat the drum with your help about how hot these areas are and how desperate employers are for the next generation of students to go into these fields.
Well, I'll add to this that our software development center in Pune, Cairo, Egypt, and Shenzhen, China, all have the same problem.
Wow.
All the same problem. Maybe worse in India, because what we're doing is because the wages in the US are higher, anyone who can bust a move and get a visa is over here. It is one of the #1 reasons why 2 areas of development have advanced so slowly is ADAS, which is autonomous navigation for passenger cars, as well as industrial mobile robotics. Have almost taken a standstill in the United States, or globally, I'll say that. Very few exceptions. It's not true. And you could reach out to me on offline and we could discuss this topic because this is a huge misperception. If that's what was being put out by high school guidance counselor, I'll be very sad about it.
It was
It's a
very
real
depressing when I heard that, but I would love to talk some more, Robert.
So I think one of the things that computer science is doing to address this is looking in non-traditional spaces for students of interest. So rather than just focusing on those people who've been programming since they were 6 years old, looking at people who have the requisite skill sets in terms of math and statistics. And actually it turns out that physics is very highly correlated with ability of students to do well in our computer science program, and looking at those students who may not be from traditionally pulled into the computer science, AI, robotics area, and making them and bringing them in and exciting them. Once they get here, they get really excited about it, and that is going to, I think, help increase the pipeline.
Well, it's really interesting what you're saying there, Reed, because my background for 10 years was in counterterrorism, then mechanical engineering, and now I'm the director of system engineering for ADAS. So anyone who tells you that they need a CS or EE degree to get started is not correct at all. In fact, most of these system level engineers who are experienced ADAS engineers in my industry started off mechanical, weirdly enough. And non-traditional degrees. I'm talking business even. There's a couple of my colleagues, like, who recently is the director of development for a division of NVIDIA. He was in automotive for a long time. Didn't go that route either. And I happen to know, having worked with, it's been a while, with Carnegie Mellon on your National Engineering, Robotics Consortium. A lot of those people were non-traditional students as well, in terms of what they studied.
I hate to put a stop to this, but we have to move on so everyone can get to their next panel. So I want to thank everyone so much for being a part of this, and our panelists, Reed, Mark, and Aaron. Thank you so much for making this day a success. And I hope you guys do reach out to each other and follow up, and definitely take on some of our students. That's our main goal for everyone here, I think. Thank you very much, and have a good afternoon.
I know.
Thank you.
Everyone.